This video presents an overview of all of the ways of calculating electric fields. The emphasis is on interpretation because there's about a half a dozen ways of calculating electric fields, so knowing which one to use is almost as important as knowing how to use each method. Sometimes it's more important to know which one to use. I'll present them in the order in which you need to think about them in an introductory course, not the order we learn them in, and probably not the order in which you would use them in a more advanced class. Some of the ones towards the end of this video are more important when you get into an advanced, say, junior level physics class or an advanced electrical engineering course. In addition, I want to be clear that some of the statements I make assume the fields are static, as is the case at the start of an introductory physics class, but not true in general. First, this isn't really a method of calculation, but rather a basic principle. And because it's sort of fundamental, the first thing we want to look at is whether or not the point we're talking about is in a conductor. If so, the field is zero, because the charges in the conductor will move until the net force is zero. If there's a non-zero field, there'll be a non-zero force, which will move the charges until they're in equilibrium. But the important detail is the difference between being in a conductor and inside of it. These little sketches have a shaded region that's meant to indicate a conductor, something that might be copper or aluminum. In the conductor means you're physically in the shaded area, that is the part that's metal. Inside might mean you're inside of a hollow conductor. The part where the field is zero is the part where it's shaded. If the charges are in static equilibrium, the field will be zero in all of those shaded areas. But it doesn't have to be zero inside, that is, in a hollow region in the conductor. That will depend on other things in the problem, like whether there's a charge in that region inside the conductor. One example of this is example 21.7 in our textbook. The shaded region is again a conductor, and the electric field is zero everywhere in that blue shaded region. But it's not zero in that interior region because there's a charge inside the conductor. The second thing I want to point out is called the principle of superposition. Again, this is not a method, but rather the way in which we will deal with multiple charges laid out in various regions in a particular problem. It says that the total field is just the vector sum of the fields produced by each source. So once we know we're not in a conductor, we need to identify each of the sources of the field and use an appropriate method for each one. As an example, here I've got both a point charge and a little line charge. E1 is the field produced by that negative point charge in the lower left, it's shown in light blue. E2 is the field you get by doing an integral over the charge distribution of that little rod, that's shown in red. The final answer is the total field E, that's the vector sum of E1 and E2. Now, you don't normally see a problem like this in an introductory level class, but it's pretty common at the next level. So using two different methods in a single problem is something that you should be aware of, even if we don't do it on our exams, for example, and maybe you don't see it in our homework. Now let's look at the methods used to do a particular thing. The first thing you want to ask yourself is a point charge? If so, the vector field E is kq over r squared r hat. And what you need to be careful to do is always follow a definite procedure, attacking each charge source as a separate problem. You're expected in this class to be able to do a point charge problem for any possible situation. That is, putting that charge anywhere in the xy plane and calculate the field at any point in the xy plane. When you're done, remember to assess your answer. Does, for example, the electric field point away from a positive charge like shown here, or point towards a negative charge? Second, is it a charge distribution? And if so, is it a distribution with symmetry? That case can be attacked with Gauss's law. This is the most common advanced method encountered in introductory classes, and it's also the first of Maxwell's equations. With Gauss's law, pay attention to each step in the IDEA approach described in Strategy 21.1, and in particular how it's applied in each of the examples in Chapter 21 and in each of the examples I do in class. You need to be able to explain the steps used to turn the integral of the flux, which is the integral of E dot dA, into, say, the field strength, ER, times the area A, for each of the symmetries. Your focus should also be on the critical thinking required to determine the Q enclosed for any particular problem. Those are sort of three different steps here. Do I have the symmetry? How do I do the field for that symmetry, and how do I determine the Q enclosed for a particular problem with that symmetry. The flux is just the integral of E dot dA, and that gets turned into a field strength times an area. For a spherical case, that area is 4 pi r squared. So you get the expression here, 4 pi r squared ER equals Q enclosed over epsilon naught. For a cylindrical case, that area is 2 pi r times the height h of the cylinder. So you get 2 pi r h times the field strength. That's equal to Q enclosed over epsilon naught. Now, what I want to emphasize, it's all in bold red face there. There is no formula, no single formula for Q enclosed. You must think and use thinking to figure out what charges are included because they happen to be inside the Gaussian surface of radius r. Number 3, if you're given a potential, V of r, when you first see this video, you won't even know what this is. But if you're given the potential, you can calculate the electric field from the negative gradient of the potential. That upside down delta there is the gradient operator. In one dimension, we'll usually do the problem in one dimension. In one dimension, it's negative derivative with respect to x times I hat. You have to put the little I hat in by hand because that's inside of the gradient operator, but if you do the derivative, you have to put it in by hand. Now, this is also how we measure electric fields in the lab, from the change in the potential divided by the change in position. And again, you calculate the strength from the change in V over change in, say, X or Y, but you have to put in the direction by hand. The direction points downhill, as shown in this picture from our textbook. I've added a nice big bold red arrow on there to show that the field lines point downhill, are always perpendicular to the lines of equal potential, and therefore away from a positive charge. Number 4, an arbitrary charge distribution, one where you can't use Gauss's law. In that case, you have no choice but to integrate over the distribution. This is one that you'll see in advanced classes for physics majors and probably for electrical engineering majors if you're following a particular track in electrical engineering. What you have to do here is basically apply the same thing we do for a point charge, but apply it to a small slice of the charge distribution, which shown as the black shaded region there labeled dq. The differential, the small piece of the electric field, is k dq over r squared r hat, although we will often, in fact almost always, use r hat equals r vector over r in these problems. Then once you've found the dE, the vector piece of the field, for that particular little piece of charge, you then just do the integral from a to b over the charge distribution from one end to the other of that differential of field. The key step of determining what is dE is identical to the steps we do for the point charge. So that's a piece that I expect you to be able to do on exams, that is set up the integral, because it's the same as a point charge problem. The only thing that's different is you have to figure out what dq is, and it's in general some charge density, lambda, that could be a function of x times dx. Number 5 is really outside the scope of a lot of things we do in this class. It's if we have a time-varying magnetic field. In that case, we use Faraday's law, which we don't encounter until chapter 27. It's also different because this is not a static field, so I'm including it here only for completeness. What's different is there is no source charge. That is, there is no charge producing the electric field. The electric field is produced by the changing magnetic field. And that electric field circulates around that magnetic field region, so that the electric field lines are tangent, the electric field vectors are tangent to the electric field lines that you see in gray. This is quite different from the case for a point charge. For a point charge, the electric fields radiate away from that charge, whereas in this case, the electric fields circulate around the region where the magnetic field is changing. The other difference is that for a point charge, the fields are static, whereas for the magnetic field case, those fields are actually changing with time. Now, if you have time-varying fields, in general, you use Maxwell's equations written in terms of vector differential operators. This method is beyond Calc 3, so it's certainly beyond the scope of this course. But again, I want to show you this for completeness. Maxwell's equations in that form look like the following. The first one is described as being the divergence of the electric field being equal to the charge density rho divided by epsilon naught. The second one is said in words as the curl of the electric field vector, and that is equal to the negative partial derivative of the magnetic field with respect to time. What the first one means is that a charge density produces an electric field that radiates away from, that is, diverges from the charge density. What the second one means is that a changing magnetic field produces an electric field that curls around, that is, circulates around the region of changing magnetic field. Now, of course, the problem is you don't know what these equations mean, and they're certainly not in the books. There's nothing in our book to help you with it. Second, in order to do this, we actually need to have the magnetic field as a function of x, y, z, and t, and we don't even know what a magnetic field is yet at this point in the course. And number three, once you've got them, you have to be able to solve partial differential equations in 4 variables, which is, again, something that you wouldn't have seen even if you've taken a differential equations course. So that's the end of this video. These pictures are modified versions of various things from various places in our textbook.